Hey guys, welcome to a new video in the Graphs and Networks video series. Today we'll be discussing about graph isomorphism. So yeah, let's start. So two graphs G1, V1 and V1, E1 and G2, V2, E2 are said to be isomorphic if there exists a bijection F from V1 to V2 such that whenever U, V belongs to E1, then that means that if and only if f of u and f of v belong to E2. So notice that this is an if and only if condition, hence that is shown by the double implied sign. So that's the basic definition of graph isomorphism. So in simple terms, two graphs are isomorphic if there exists a function that is a bijection, and to recall, a bijection is a function that is 1 1 and on 2. So it's injective and surjective. So f is such function, and it goes from your first vertex at 1 to your vertex at 2, and if this function exists such that the adjacency and non-adjacency is preserved, then we say that the graphs are isomorphic. So here's a small note that graph isomorphism is an equivalence relation. And what do you mean by equivalence is that relation is symmetric, reflexive and transitive. So all three should hold at the same time to be called an equivalence relation. Alright, so let's illustrate the definition by an example. Say you got your C5 here. So this is C5, a cycle of 5 vertices, and those are labeled by P, Q, R, S and T. Those are the white dots here. And say we've got another graph here. So say this is G1 and this is G2, and this is sort of like a star, right? Shape of a star, and I've labeled it as X, Y, Z, U and V. Okay, now what I'm going to say is let the bijection be that f of p, when you apply the bijection on vertex p, it transforms and points to vertex X. Alright. Similarly for q, f of q equals z, f of r equals v, f of s equals y, and f of t equals u. So I'm defining the bijection to be like this and mapping the individual vertices of my graph G1 to my graph G2. And if you see, say take graph G1, you see that p is adjacent to q and t, and in graph G2 f of p, that is x, is adjacent to f of t and f of q, that is u and z. So x is adjacent to u and z. So that means that adjacency is preserved in this bijection. Okay, and since adjacency is preserved and this is a bijection because it is injective and surjective, we say that these two graphs are isomorphic. Okay, so I've prepared a small visualization to make you see and observe how we convert this graph to this graph. So you can, this is sort of like a visualization of your bijection and how we move and transform all the vertices and map it to make this graph G2. Okay, so you've got a graph G1 as it is, as shown here. This is your graph G1, and now what I'm going to do is I'm going to pick up point P and bring it down here, illustrated by this blue arrow, dotted arrow, and I'm going to keep the edges intact. So all the connections remain same. I'm just moving the vertex, grabbing that point and shifting it down below edge SR. So you get something that looks like this here. You get something that looks like this. So that's the same thing. So now what I'm going to do is I'm going to twist edge SR. I'm going to twist edge SR such that the edge is intact. But what I'm going to do is I'm going to switch their positions so that T is connected to S and Q is connected to R. That is still there, but they look like something when you they intersect, basically, if you want to think of it like that. So you get something like this as shown here. You see that T is still connected to S, S is still connected to R, and R is still connected to Q, but that the positions of R and S have been interchanged. So that was my objective. Now what I'm going to do next is I'm going to flip this whole segment upward. So I'm going to take it and I'm going to flip this whole segment upwards. If you do that, you would get something that looks like this. So T is still connected to S, but S is now above Q, and S is still connected to R, and R is still connected to Q, and since we're flipping it upwards, R is above Q but still connected to it. So you get something that looks like this. Now what I'm going to do, first I shifted, in my first step I shifted P downwards. I'm going to reverse that, I'm going to shift it up now. Alright, so shift only vertex P upwards while keeping the edges intact. So if I shift P upwards, you get something that looks like this, which is your final graph G2. So bingo, you got your graph G2, and this was a rough visualization of your transformations that you perform on G1 to get G2. Alright, so this was a step-by-step visualization of the bijection function that transforms and maps every vertex of graph G1 to graph G2. Okay, so for more complex graphs, it is not easy to see or figure out a bijection just by observing a graph. So in this graph we had only 5 vertices. Say you have got a graph with 10, 20 or 30 vertices. You cannot figure out the bijection by just looking at the graph. It is not possible. So to check isomorphism for such questions, we use graph invariants. So a graph invariant is a property of your graph that is preserved by isomorphism. So say when you take this example that we just saw, and in C5 you've got 5 vertices, and in your isomorphic graph you've also got 5 vertices, right? So that means that the number of vertices haven't changed when you applied your transformations and you got your isomorphic graph. So that property is called an invariant. It does not change and it is preserved when you perform your transformations. Okay, so we use graph invariants to check for isomorphism. Okay, so these are generally the following graph invariants that are used to check for isomorphism. The first one is the number of edges. So that means that the number of edges in your graph G1 and your isomorphic graph G2 are same. Similarly, your number of vertices are also same in your isomorphic graphs, and your degree sequence of both the graphs, your graph G1 and your isomorphic graph G2, should be same. And the fourth point is that the same number of circuit of particular length. Okay, so that means that if you've got a big graph of say 10 or 15 vertices and you've got a small cycle in it of say 4 or 5 vertices, say you've got a 15 vertex graph, and in that graph you've got a cycle of length 5. So that means that in your isomorphic graph there should also exist a cycle of length 5. Okay, and this is applicable to all the cycles in your original graph, that should be the same in your isomorphic graph. Okay, so usually checking the first 3 conditions is usually enough to see whether both the graphs are isomorphic or not. Okay, so let's do one question. So this is a GATE computer science question asked in 2012. So the question is like this: you've got your graph here, this is your original graph, and it says that find the graph isomorphic to the given graph. So this is your given graph. So, and you've got your 4 options as A, B, C and D. Okay, so what you do, first of all, in your original graph given in your question, I want to list down the number of vertices, the number of edges, its degree sequence, and see if it has got any cycles or not. Okay, so first of all, the number of vertices in this graph are 8. I'm going to label them. Okay, 1, 2, 3, 4, 5, 6, 7 and 8. You see there are 8 vertices. Similarly, if you count, there are 8 edges, and the degree sequence for this graph is illustrated below. So vertex 3 has degree 4, and you see that there are 5 vertices having degree 2. Alright, so that's how I've written the degree sequence. If you don't know what a degree sequence is, I'll suggest you go through my earlier video on degree sequence, and so you'll get a fair idea of that. I'll attach that I banner on top, so go check that out if you don't know what a degree sequence is. Next up, I listed down what all cycles I have in my graph. So I've got one 5 cycle, and this 5 cycle is made up of vertices 3, 4, 5, 6, 7. So joining them, I've got my 5 cycle, as you can see. Okay, now let's list down all these properties of all the options and see which option matches every property of our original graph. Okay, so for option A, you've got your graph given like this, And so listing down all the properties, we have mod v as 8, mod e as 8, degree sequence as this. So I always degree sequence is generally written in decreasing order, so I've followed that convention. So I've written my degree sequence, and I've seen that there is a 1-3 cycle here illustrated by this. So this is a 3 cycle that you see. So now comparing, we see that the number of edges and vertices are same, but you see that your degree sequence and the number of cycle of particular length are different. So that means that option A is not isomorphic. Now let's check for option B. You see that your number of vertices are 8, edges are 8, degree sequence is mentioned. You can check that out. It is correct, what I've written. And you see that you've got a 5 cycle. So it's not really easy to get it at first, but if you can see carefully, this is your 5 cycle illustrated in green. So these are 5 vertices, and this is a 5 cycle that you have. Now if you see carefully, we've got your all these features the same as our original graph. So that means that B is our isomorphic graph. Also, you also have to check for all the options, as it may be a multi-correct question. So I'll just check through all the options as well. So for our graph C, we've got mod V as 8, mod E as 8, you've got a degree sequence as this, and you see that there is one 5 cycle present. So this is your 5 cycle. Now what you see is that your mod V, mod E and the number of cycles of that particular length are same, but your degree sequence is differing. So that means that option C is not isomorphic to our original graph. Now looking at option D, it's very easy to figure out that this is also not isomorphic because of the degree of the 4 cycle present. We have to have a 5 cycle to make it isomorphic, but we only have a 4 cycle. Alright, rest all features are same, but since this isn't same, we can't say that this is isomorphic. So that means our correct answer is option B. So that's it for this video. If you found it helpful or insightful in any way or form, make sure to smash that like button, subscribe to the channel for more content, and yeah, I'll see you guys in the next video. And go check out the my previous videos and the graphs and networks tutorial. I'll attach the link in the bio and on the screen. So yeah, see you guys. Bye bye.